Okay, so we've got this following example. It says, consider the following data which has been collected on diet, activity, and living arrangements. We asked 100 different people who live alone and 100 people who live with others about their eating habits. And we recorded here whether they said they were on a strict diet, whether they watch what they eat, or whether they eat whatever they feel like, okay? And we're gonna go through and conduct an appropriate chi-squared test with 95% confidence. And what you'll notice here is that these two numbers, or the row totals, are fixed, right? Which means that it's appropriate to do a test of homogeneity here, okay? As opposed to a test of independence or a test of goodness of fit, okay? So because the row totals are fixed, we can go through and compare the distributions between the two groups, right? So we're gonna look at, the proportion here that fall on a strict diet, the proportion that watch what they eat, and the proportion who eat whatever they feel like. We're gonna look at the proportion that falls within that group, each of those groups, or the distribution across the different eating or diet habits between living alone and living with others. So in particular, the null hypothesis is going to be that the distribution in diet or eating habits is the same between the two different living arrangements. So I'll write that here. The distribution in diet or eating habits is the same amongst those living alone and those living with others. Okay. And then the alternative hypothesis is going to be that the distributions are different. Okay. So something like the distribution in diet, eating habits is different between those living alone and those living with others. So you'll notice that this null and alternative hypothesis is slightly different than the null and the alternative hypothesis for a test of independence. For a test of independence, we use when the overall total is fixed. We're talking about whether there's an association or not. And we can't go that far on a test of homogeneity. We're limited by the fact that only our row totals are fixed. So this is the appropriate null and alternative hypothesis. Some textbooks will go through and talk about, the proportion on each of the different groups as being the same, right? So they'll say like P1 is equal to P2 is equal to P3, right? Where P1 is the proportion on a diet, the proportion watching what they eat, and P3 is the portion who eat whatever they feel like. And then the alternative here will be, at least one of the P's is different or something like that between the two groups, right? So sometimes that's the more sort of mathematical way of writing it. Maybe I should also add in here for both groups. And then I'll say at least one P is different for one group or something like that. Something like that, okay? But usually I just talk about the distributions. Okay, so you're gonna need some kind of computational tool to help you to be able to work this out. So if you're an R user, I'll just pull that up now. Okay, and so the key here on this is that you're gonna have to go through and enter in the table. So I'm gonna use the code table, and then I'm gonna create a matrix, okay? Inside a concatenated vector, so we do C, and then in brackets, you're gonna put in all the numbers in the table. So remember, you put in the numbers in the table, but not the total rows. Okay, so in this case, this one has 2 rows and 3 columns. And to enter in the data, we always go down the columns. So I'm going to say 6, 8, 72, 49, oops, 49, 22, 42. Okay, so there's the numbers entered in the table. Then we have to tell it the number of rows is 2 and the number of columns is 3. And so if I enter that in, now I've got my data entered in as table. If you wanted to see the table, you just type table and then enter, and you can see that you've entered the data in properly. Okay. And then our code to run a chi-square test on this is chisq.test. Okay. So we're going to run a chi-square test on table. The only sort of caveat is after table, you have to put correct is equal to false. There's a correction that they do, especially if it's a small sample size. And if we do that, it won't match with what the calculator does and what the textbook will want. So just use the option here, correct is equal to false. And if I run that, it's going to spit out a lot of different things here. But I've got my test statistic, which is 10.903. So maybe I'll just write this in here, right? So my chi-squared test statistic, oops. So my test stat is 10.903. It follows a chi-squared distribution with 2 degrees of freedom. Remember, the degrees of freedom comes from the number of rows minus 1 times the number of columns minus 1. So in this case, it was 3 minus 1 times 2 minus 1, which ended up giving us 2. But again, just use the calculator to work it out. And this corresponds to a p-value of 0.00429. Okay. And if I wanted to draw a little picture here, right, there's my chi-square distribution. There's my test statistic of 10.903, and my p-value represents the area to the right there. Okay, so chi-square tests always do the area to the right. And based on this, we can make some conclusions, which we'll do in a second. Actually, maybe I'll do that now for our folks so that you don't have to watch the rest of the video. So with this p-value, right, you're going to compare that to the alpha that they gave. Okay. And so they said they wanted to do this test with 95% confidence. Okay. And so here, that means that alpha is equal to 0.05. And so you can compare your p-value to your alpha. In this case, the p-value is much smaller than your alpha, which means we have significant evidence for the alternative. We're going to reject H0, and we have significant evidence for the alternative. So we have significant evidence here to suggest that the distribution in eating habits is different between those living alone and those living with others. We can't say for sure that that's the cause of the difference in the distributions, but that's certainly something that's going on here, right? So in this case, it seems like yeah, it seems like actually those that live with others say that they eat whatever they feel like more, whereas those living alone have more that are actually watching what they eat. So that's sort of interesting to me. But again, either way, we're not going to speculate as to why. That's somebody else's job. But we do have significant evidence here to say that the distribution is different. I'll write that out at the end of the video. But first, I want to pull up the calculator. So what we need to do is we need to enter this data into our calculator. So let me just pull this over so you can see everything all at once here. Okay. So I have to go through and enter in this sort of 3x2 table here. I'm going to need to do that inside the matrices. So I'm going to go to second and then matrix. So in matrix A, I'm going to put the observed values. So I have to go over to edit, and I want to edit matrix A. In this case, I want it to be, I can never remember with the order here. 3x2? Nope, that's not right. We want 2 rows and 3 columns. So we need it to be 2x3. There we go. Okay. And then you need to enter in these numbers. So we've got 6 and then 72 and then 22, oops, 22, and then 8, and then 49, and then 42. Okay, so that's my observed matrix, and that's now sitting there in matrix A. So if I go to second and then matrix, you can see that matrix A is saved there. It's this 2 by 3. Okay, in matrix B, we have to put the expected values. Okay, now I could go over to edit and press edit, and again, I want it to be 2 by 3. Okay. Now inside here, we have to put the expected values, and it might take us a little bit of work to figure out what those are. So I have the row totals, but maybe I should go through and just get the column totals here. So I've got 6 times 8, or 6 plus 8 gives me 14. 72 and 49 gives me 121, I think. I should get my calculator out. And then 22 plus 42 gives me 64. So hopefully that all adds to give me 200. Let me just plug that into my calculator here just to make sure. So I've got 14 plus 121 plus 64. Oh no, I'm short one. So where did I screw up? Oh, maybe the numbers I never added to 100 anyway. That would be hilarious. Okay, so let me try 6 plus 72 plus 22 gives me 100. 8 plus 49 plus 42 gives me 99. Oh, okay, so let me go through and fix this here. Let's make this number 99. It shouldn't change anything about the calculations really, but it really means we only asked 199 people. Bummer. Okay. And that happens sometimes in reality, right? Maybe we go through and ask 100 people, but then, you know, this one person in this one group decides to withdraw their consent. They don't want to be part of the study anymore. And so then we end up with weird uneven numbers. So I don't think that's what happened here. I think I just wrote the wrong numbers, but the reality is this does happen sometimes. Okay, so we need to work out the expected values here. So the expected value here for, maybe I'll just do this cell here. The expected value for this cell here, right? I'm going to do 100, that's the row total, times the column total, which is 14, and then I'm going to divide by 199. Okay, and this is going to get kind of messy because we're going to get decimals here. So let's do everything to one decimal place. So I'll do 7.0. Okay, and the next one, maybe I'll just fill these all in here. So for the 72, those that are watching what they eat and live alone, the row total is 100 times 121 is the column total, divided by 199 gives me 60.8. Okay. And then for the 22, we do 100 times 64 divided by 199. So this gives me 32.2 if I round. The next row, we've got 99 times 14 divided by 199 gives me 6 point, and then, oops, it'd be 6 point, okay, so this is going to be 7.0 if I round. And then we've got, oh, you know what? This is going to end up being the same because we've got 99 times 121 divided by 199. Okay, so this one will also be, this one will be 60.2 if I round. And then 199 times, oops, sorry, 99 times 64 divided by 199 gives me 31.8. Okay. So if the row totals were exactly the same in this case, what you'll find is that the proportion or the expected numbers will be the same in both of these rows. In this case, the 100 and the 99 are very, very close. So what you're noticing is the expected numbers are very, very close, though not exactly the same because they're slightly different numbers in the row totals. So I'm going to enter these into my calculator here. So I've got 7 and then 60.8 and then 32.2 and then 7 and 60.2 and 31.8. Perfect. Okay, so in matrix B, I've saved the expected values. In matrix A is the observed values. And so if I go to stat and then over to tests, you're going to go down to a chi-squared test. It should be down here. There it is, chi-squared test. Chi-squared test is the one that we're going to use for both the test of homogeneity and the test of independence. So we'll do chi-squared tests. My observed are in the matrix A, my expected are in matrix B, and I go through and press calculate, and it does give me the same thing that R gave me before. So my test statistic here is 10.903 if I round. My p-value is 0.00429. It also tells us the degrees of freedom is 2. So we're going to end up making the same conclusions here, that we're going to reject the null hypothesis and conclude that there's significant evidence for the alternative. And I should just write out here specifically what that is so that everybody has it. And I'll just do it down here in a different color. So something like the p-value is less than alpha, so we're going to reject H naught. We have significant evidence to suggest the distribution in diet eating habits is different between those living alone and those living with others. Sorry, that's super small, but oh, and you can't even see it. Haha. Oh well. I'll just read it out loud. It says there's significant evidence to suggest the distribution in diet eating habits is different between those living alone and those living with others. So that's basically how I would go through and do a test of homogeneity.